by body oxygen, absorption oxygen by body. Human being. Absorption oxygen from air and removal carbon dioxide. And removal carbon dioxide. It includes not only lungs ventilation. It includes 5 stages. You must know these 5 stages. What are the stages? The first stage is called lung ventilation. You call it breathing. No, nafas, like nafas. Breathing. Breathing. First stage, lungs ventilation. Lungs ventilation. Ventilation. Ventilation means incoming oxygen into lung and remove. No, air. Air goes into lungs, and come back. Both processes. Ventilation. Ventilation means renewal of air inside lung. Second process is called gas exchange. Gas exchange. The thinner membrane of lung cells, alveoli, has a stick contact with the interstitial fluid and blood vessels, and it provides gas exchange across lungs membrane. It's called lungs membrane or lungs barrier. Alveoli, alveolus, example, alveolus. Alveolus, interstitial fluid, and capillary. Capillary. And gas exchange. Oxygen travels into lungs, right? into bloodstream, and carbon dioxide is removed. Carbon dioxide opposite into alveolus. Gas exchange. To provide delivery of oxygen into bloodstream and then transport to tissues. Two processes are called external breathing, external respiration. External respiration. It's very important. External. It includes lungs ventilation with convection, diffusion of air deeply into lungs, and then gas exchange, external respiration. The word breathing is considered like lungs ventilation. The same, breathing. Next processes. Next stage of respiration is included to the next part, internal respiration. It contains compounds for each stage. First, transport gases, oxygen, carbon dioxide in the bloodstream, in the blood stream. Next, gas exchange between blood and tissue cells, working cells. Again, gas exchange, but gas exchange in systemic circulation. Gas exchange between blood and tissues. tissues. Tissues, and the last stage is called cellular respiration. Cellular respiration. You must know exactly 5 stages. First 2 are related to external respiration, and the next are related to internal respiration.
Cellular respiration, Krebs cycle.
Tissue respiration. It includes the Krebs cycle.
Krebs cycle.
Yes, Krebs cycle. There's absorption after force, the absorption of oxygen, intercellular processes, oxidation, and release carbon dioxide. Then, at first, now function of lung, I'm going to not explain function of lungs because it's simple. I want to pay focus today to more complicated processes to explain it. First, breathing. How does it happen? Mechanics. Breathing mechanic. Why air goes into lungs during inhalation or inspiration and goes out during opposite process, exhalation or expiration. Why? It depends on some physical forces. I should draw a scheme of lungs. Now, first about anatomy. Did you study anatomy of lungs? Anatomy of lungs and airway. There are upper airway until larynx. Starting from larynx and deeper, they are called lower airway. Lower airways. We are going to talk about lower airways. Trachea, large bronchi, and next. How many generations each airway tube is divided to two branches, each. Half. And how many generations does it have? How many generations? How many times? Just one. 10? One? How many generations from trachea to the end?
Many.
How many?
A lot of.
Count.
A lot of.
23.
20?
23 generation. 23 to makes a largest surface providing gas exchange. 23 generation. I pay attention because first, from the first until 16th generation, airways don't contain alveoli, no alveoli. So gas exchange here doesn't happen. It's called conducting zone and provides anatomical dead space. Do you know dead space? Dead space. Dead space means volume of gas, air. Not having gas exchange, without gas exchange. Missed. Dead space, anatomical dead space. The volume of anatomical dead space, average volume in adult person, about 150 milliliters. But this air has some significance. To heat air, for example, cool air from environment, to heat, to clean, to provide some reflexes, sensory function. It's not useless. It's an important part. Then next generation, from 17 until 19th generation. Here, respiratory bronchiolitis. Respiratory respiratory, bronchioles, small bronchioles having single alveoli. They have a few alveoli. Bronchioles, and maybe here it has some alveoles. A few of alveoles. Here, the first step of gas exchange. Gas exchange is starting here, begins here. And main respiratory zone from 20 until 23 generation is the main gas exchange, high gas exchange, high rate of gas exchange, main gas exchange, due to a large surface. Providing high rate of gas exchange. So two zones, conducting zone without alveoli and respiratory zone, two zones. Not all alveoli provide gas exchange in any given moment. Because some alveoli don't have enough bloodstream in surround capillaries, alveoli must have enough contact with bloodstream. But sometimes that's normal situation. Capillaries, enough Q inside capillaries. It's called perfusion. Perfusion, blood volume, delivering blood into organ, into tissue. This is normal perfusion, but sometimes it may be a next situation. When alveoli is ventilated well, but here there is vasoconstriction and lower perfusion.
Collapse.
Maybe not called vasoconstriction. It's no blood in capillaries. Vasoconstriction, no perfusion. But ventilation, okay, no perfusion. So gas exchange doesn't happen. And another situation, perfusion, okay. But some parts of lungs may be not ventilated enough, and here collapse of some alveoli, even a normal healthy person. No ventilation. Ventilation we will mark with V. Here V means ventilation in pulmonary sense. So three situations. Lower is good situation, lowest is another situation, there is no gas exchange. And lungs, local mechanism control ratio between perfusion, Q, and ventilation. If some part of lungs is not ventilated well, this part constricts blood vessels. And opposite, no perfusion, it decreases ventilation by constriction of some bronchioles. It's local mechanism, coordinated, normal coincidence between ventilation and perfusion, because it's more effective. For example, when you are in the upright position, standing, sitting, upright position, your breathing system works more effectively in the area of the lung bottom. Bottom. Here bottom.
Base.
Here bottom. Here top, bottom. This lower part of lungs is ventilated better than top. So here ventilation is better and perfusion better. Why perfusion better? Because due to gravity force. If you're lying in bed, opposite, another situation, a lower part of lungs will be ventilated and perfused more compared with upper part due to gravity force and combination between pressure inside lung. Then about mechanics, breathing mechanics, very important to understand. Again, I will draw a scheme of one lung. Lung is covered by a special pleural tissue. It's called pleura. Pleura has two layers, visceral layers. Yes, connected with lungs. It sticks with lungs, and parietal. Parietal, pleura. Between two layers, there is fluid between two layers, intrapleural. This space between intrapleural fluid. This space is called intrapleural cavity or pleural cavity. Intrapleural space. Intrapleural space. It is filled by fluid. What is the difference in pressure, air pressure, and pressure inside lungs and inside intrapleural space? We speak about pressure, partial pressure. Before we had
one minus pressure and
minus means negative compared to atmospheric pressure. I will explain because it's important. How can we measure gas content? Content of soluble ions we measure with concentration. Concentration millimole, for example, concentration gradient. Water content we can measure osmotic pressure by osmotic pressure. But here we have deal with the concentration of gases. It is measured by partial pressure. Air, atmospheric air, an external environment on the sea level is important. At the high altitude and mountains, air, sea level. Atmospheric partial pressure. Atmospheric pressure 760 millimeter Pg mercury. But do you remember composition of air? What is the main gas?
nitrogen.
Nitrogen, it weighs 1% oxygen and a little carbon dioxide. Partial pressure, oxygen inside atmospheric pressure will be about 160 millimeter G. And partial pressure carbon dioxide, very little, 0.03. It's air, partial pressure. And intrapleural pressure is here, bronchi, entrance. Simple scheme of entrance into lung. Air. 760 millimeter G. Atmospheric pressure. It can go inside, but before inspiration, pressure inside lungs, it's called alveolar pressure, PA. Before inspiration equal same atmospheric. Before inspiration. Until aspiration. When you don't have breathing, it means equal pressure between air outside and inside. So no gradient, no pressure gradient, and no movement of air. Intrapleural pressure between inspiration, no, breathing, before, between breathing, initial. Intrapleural pressure, it's marked by PL, equal value lower than atmospheric pressure, about approximately 3 millimeters G. This 760 minus 3. And here, like atmospheric minus 3. But it's average number, not absolute number, because different part of lung may have a little different numbers. Minus 10, minus 2, it's average. Moreover, you can see in textbook minus 5, why average? Because it depends on unit. Now I say in millimeter G, but sometimes it's measured in centimeter water. Centimeter water, 1 centimeter of water equal 1.36 millimeter G. You see, like this. You see, I will talk just about millimeter G. Don't confuse. Millimeter G. So 757 about it. Minus 3 here is a relative, not absolute. If you put inside intrapleural pressure, measuring
Hemothorax, such as hemothorax.
Stop, wait. Hemothorax, yes, thank you. What forces create negative, in relation to atmospheric pressure, negative lower pressure inside intrapleural space. Why? Because lungs are influenced by two principal forces. I will draw it and copy with me. Two forces. This is chest wall by influenced two principal forces. Elastic recoils. First, elastic recoil of lung. No elastic recoil. Elastic recoil. Its force provided by elastic fibers, collagen, elastin of lungs, and surfactant. This force is directed to the center lungs, and if you take lungs from the body, lungs decrease volume and collapse due to elastic recoil of lungs. Chest wall has also elastic recoil. Opposing force, elastic recoil of chest wall. How to call that? The long. No, ER lungs. Elastic recoil of lungs and elastic recoil chest walls. Elastic recoil of chest walls is directed mostly to outside, but it depends on deepness breathing. During very deep breathing, elastic recoil of your chest wall can be inverted. But now we are talking about normal breathing, quiet breathing. These were two forces affecting lungs and stretch lung. A balance between two forces. Stretch lungs. Pneumothorax.
External muscle, rib.
External muscles, intercostals. External intercostal muscles between rib and diaphragm have tonic activity even without breathing. When you don't breathe, anyway, this muscle has tonic activity. You can put here, and muscle tonus of respiratory muscles. Respiratory muscles. Main respiratory muscles, diaphragm. Actually, there are two processes: inhalation, inspiration, and opposite exhalation. Inhalation requires diaphragm and intercostal muscles. Intercostal muscle located between ribs. External intercostal. Quiet expiration is passive without muscle. Without muscle, it doesn't require energy. So respiratory muscle more important. Diaphragm and external intercostal more important. If you has lesion, damage of this membrane, it's called pneumothorax. Pneumothorax, for example, knife injury, damage pleura, and these forces become separated. What happens with lungs? Collapse. Lungs decrease volume, but chest wall increase volume. For example, a person with emphysema, next course now is a study, my past student studying pathophysiology, restrictive obstructive diseases emphysema. For example, emphysema is obstructive disease. During emphysema pathology, emphysema means destruction of walls between adjacent alveoli. Alveoli becomes more and decrease elastic force. So this force is decreased. What happens with chest wall in a patient with emphysema? It becomes small. This chest wall becomes small. That's one of symptoms. Depends on stage. So in normal person, these forces have balance, and this balance defines lung volume.
Capacité sinir bir papırsız ki capacité sinir kabukari.
I need to see letters. So my brain, right and the left hemisphere, always must associate, combine. It's about what?
Emphysem disease.
Why?
Because capacité sinir kabukari. Keep on chest.
Chest.
Capacité. Trans. Trans. Sinir trans or chest.
Kabuter globe.
Because the pigeon has a big chest. It's the same here. Now you understand why. It's even simple. Because elastic recoil of lungs decreased compared with normal person. So balance shift to elastic recoil of chest wall and spans more. Then what happens during inhalation, expiration? What is the biomechanics? At first, contraction of diaphragm. Diaphragm is located here. lungs, diaphragm contracts and becomes flat. Diaphragm becomes flat. It expands chest. Expand chest. Chest becomes wider, larger. Intrapleural, intrapleural pressure becomes lower because we have to balance more difference. What does it mean? During inhalation, these forms increase during inhalation. It's muscle contraction increases this component. It just expands chest cavity, and intrapleural pressure becomes lower. I will clean it and draw a very important graph, copy with me, because I will ask during calculus. Very important. Scheme. What happens with intrapleural pressure and alveolar pressure? Two key pressures. Pressure stretching lungs outside, from outside, and pressure inside lungs. So you can stretch from inside and from outside. So two key pressure, graph of two pressure in millimeter regime. Zero. Zero is not absolute, it's a relative number. It means atmospheric pressure. Why zero? Because it's a relative point due to different atmospheric pressure. For example, atmospheric pressure at Moscow is about 750, not 60. It can shift during change weather. You can see in the forecast atmospheric pressure. It can be shift to 6 millimeter G, up, down. It's relative. Now, relative flow. Before inspiration and expiration. Before inspiration, negative intrapleural pressure, about -3. Then during inspiration, when you contract muscles, it decreases until the end. Until the end of muscle contraction and inspiration, until about -6 millimeter G. During quiet breathing. Now I show quiet breathing. Quiet breathing. Your usual breathing. Atmospheric pressure. What is atmospheric pressure between inspiration? It's equal atmospheric. So alveolar pressure will be like atmospheric pressure. What happens during respiration? When expand chest wall, it stretches lungs, volume of lungs increases, so pressure inside lung decreases in accordance with Boyle-Marriott law. By Boyle-Marriott law means partial pressure gains air multiply volume equal second situation. Inspiration, volume lungs increase, partial pressure decrease, of course. So partial pressure decreases a little, about -1 millimeter G, and it starts, because we have pressure gradient between atmospheric pressure and pressure inside lungs. It starts force air to go inside lungs, into lungs. Then air fill lungs, and at the end of inspiration, atmospheric pressure becomes Yes, equal, not atmospheric, alveolar pressure, sorry. So, mark interpleural pressure, pleural pressure, and alveolar pressure. The expiration. During expiration, expiration is passive. To provide quiet expiration, exhalation, it's necessary only to relax diaphragm and external intercostal muscle, inspiratory muscle, only to relax. And everything happens in opposite direction. Interpleural pressure becomes equal -3. Come back. In this case, what happens in lungs at the end of inspiration, here at this point? Elastic recoil lung rises, which the lungs becomes more, surfactant work less, elastic fiber has more tension, elastic recoil of lungs increases. So, during relaxation of inspiratory muscle, interpleural pressure becomes less, and it decreases volume of lung. These lungs are directed to decrease volume. When lung decrease volume, pressure inside lungs becomes more. So during expiration, we have opening process, increase, again +1, and then come back. Easy. Copy. Open your paper by hands, drawing by hands to memorize. I advise to do it. This is the dynamics of key pressure. And pressure difference between intrapleural pressure and intrapleural pressure. Intrapleural. Yeah. Difference between intrapleural pressure and alveolar pressure defines lung volume. It's called transpulmonary pressure. Transpulmonary pressure. It's very important for medicine. Transpulmonary pressure. Transpulmonary pressure. Transpulmonary pressure. Do you understand it? Transpulmonary pressure is only difference between 2 points, between 2 graphs. Kind of balance between, not balance, difference. A difference between intrapleural pressure and alveolar pressure defines position of lung. About elastic recoil of lung. Elastic recoil of lung defined by 2 factors. Elastic fibers. Elastic recoil depends on elastic fibers, collagen, elastin fibers by 1/3, and to third special substance, it's called surfactant.
Surfactant, surface stretching in the alveolar.
Yes, surfactant covers
alveolar
internal, not external, internal part, not external. Alveolus, and surfactant is here, inside.
Inside, yes.
Inside, yeah.
Decrease
Surface
stretching.
tension decreases surface tension. Surfactant decreases surface tension. Surface tension.
Turbulent attached to
Surface
collapse.
yes. No, so what is a surface tension from physics? If you have, for example, water drop, What water
Colors.
drop, you touch water drops. Water drops can follow your pad. It's due to surface tension. The surfactant consists of mostly lipids and a little proteins. But activity of surfactant, influence of surfactant is not equal during inspiration and expiration. During inspiration, put here, surfactant becomes less active. So here, surfactant less active, elastic recoil rises. Because molecules of surfactant become separated. During expiration, inhalation, surfactant becomes more and more effective. It prevents collapse. The surfactant is more active during expiration. I should write it. Surfactant is more active during expiration. Expiration to decrease surface tension and prevent collapse. The surfactant is more active during expiration. Surfactant. Well,
The children are early term. It doesn't have surfactant, but
Yes. Some newborn child, surfactant was discovered due to this problem. Some newborns dead due to lack of breathing. Why? Because ventilation was not sufficient. Why? Due to absence of surfactant or lack of surfactant. Surfactant has another function. It has
Using
protective.
shampoo too. Using shampoo too, surfactant.
No, like this. Surfactant facilitates diffusion of oxygen and has protective function. But this function is
şampuan mı sıvadın işte?
yes.
It's very
Shampoo influence for self-detention also. Well, I say it, okay. Next. About spirometry. Spirometry is a very important test. You must know main volume. You will use it in medicine later. Spirometry. Spirometry is common medical test to estimate capacity of breathing system. Respiratory system actually includes lungs with airways, muscles, inspiratory and expiratory muscles. Expiratory muscles work during forced expiration, deep breathing, and pulmonary circulation. And common medical test is spirometry. Spirometry is a test device with tube, sterilized tube. Patient take tube into mouth, close nose, and breathe into tube. Device measure volume of inspiration, expiration. And you must know spirometry curve. Copy with me again. Spirometry. Person, patient, here drum, tube, and device. And
Spirometry.
inspiration out. It's a simple spirometer, simple spirometer. It may be a small device or a bigger device, hand spirometer or medicine, hospital spirometer. But idea is this. At first, quiet breathing. But spirometer must be calibrated before at the beginning of each day. Calibrated again because it may have artifacts. But it's a details of practice. Spirometer. When you breathe quietly, your normal breathing. it records this curve. This curve, normal breathing. Usually inspiration is a little shorter, expiration a little longer, but it's not important here. Name of volume inhaled and exhaled during quiet breathing is called tidal volume. Tidal volume. Its value, normal value, about 0.5 liter. This value total, 0.5 liter. For example, if you have a simple spirometer that measures only expired volume, you inspire from atmospheric air, from external environment, close nose, and exhale this spirometer. It's measure tidal volume. But this method,
500 millimeter.
500 milliliter or 0.5, it's the same. 500 milliliter. You can measure milliliter or parts of it. Then you ask patient to make deeper inhalation, very deeper inhalation, and then exhale slowly, quiet, slowly, as this patient can do it as possible, deeper, deeper.
IRB? It's IR.
Yes. The additional volume the patient can inhale more than tidal volume. It's called inspiratory reserve volume. Inspiratory reserve volume. Additional volume that patient can exhale after normal quiet breathing is called expiratory reserve volume. Together, these three volumes are called vital capacity. Very important indices, parameter, medical parameter. Vital capacity. Vital capacity. Vital capacity. Capacity.
400?
It may be between 3-5, no, approximately 3-5 liter, depends on person, gender, height, height, of course, tall. Person has more normal vital capacity. It's maybe different. And after deepest exhalation, lungs contain some volume. This remained volume is called residual volume. Residual volume. Residual volume. It exists always. Its number, its value, it's about 150 liters. Depends. Average. And total sum vital capacity and residual volume, it's called total lung capacity. This graph may be divided to two zones. Inspiratory capacity, IC, and functional residual capacity. But volume and functional residual capacity and residual volume are very important to diagnose obstructive or restrictive lung disease. And after this test, slow vital capacity, doctor usually asks patient to repeat maneuver, but to exhale very quickly. The same. Tidal volume, deep, yeah, again, deep, slowly, slow, deep inspiration, and then a patient must exhale with high speed, quickly. And in this case, speed of inspiration will be faster, and vital capacity usually is less than usual vital capacity. Its vital capacity is called forced vital capacity. Forced vital capacity is very important test to diagnose obstructive diseases like asthma, bronchitis, emphysema. We will do it on computer, virtual experiment. Virtual experiment in normal patient with emphysema, patient with bronchitis. Значит, forced vital capacity usually is less than slow vital capacity. Why? Due to force expiration, intrapleural pressure, the forced expiration includes a lot of expiratory muscles to provide fast expiration. And due to this maneuver, this test, intrapleural pressure becomes positive. Forced vital capacity test becomes positive, and it can close some small alveoli, some small bronchi, small bronchioles, and it decreases vital capacity due to dynamic closure of respiratory airways. Due to dynamic closure. Closing respiratory airways. But it's not crucial in normal healthy person, but it may be crucial in person with obstructive disease. Dynamic closure respiratory airways and increase airway resistance. In normal person is a little difference, but in person, for example, asthma for bronchitis decreases diameter of respiratory airways. It makes tubes narrow, smaller, so it increases airway resistance and it decreases speed of expiration. So it decreases forced vital capacity. And medicine, doctor defines very important part of forced vital capacity. It's start maneuver. Amount of expired air during first second on forced vital capacity. First second here, how many milliliter a patient exhaled during first second. It's called FEV1, forced expiratory volume for 1 second. Forced expiratory volume for 1 second, forced vital capacity, and its ratio, very important medicine. Well, теперь about, it's okay about mechanic, теперь about breathing control, regulation, restriction. Now you must know this exactly, this curve, draw this curve and mark volume and know their names. Volume of air inhaled and exhaled during one quiet breathing.
volume of inhale plus the volume of exhale in normal situation.
Normal. Normal, and it exists always. It's your normal breathing. A normal person, it will be about 500 milliliters.
We have to sum two this volume together, yes?
Yes.
Inhalation and
Yes,
exhalation.
It provides ventilation, pre-ventilation. Of course, during physical exercise, person uses reserved volumes, and brain increases rate, frequency, and rate and volumes during breathing. It's called hyperventilation. Next, gas transport. This is external breathing, gas exchange. It's a big topic. I explained now everything about the first stage of respiration, lung ventilation. The next stage of external respiration, gas exchange. Shortly, what force provides gas exchange? Again, I draw alveolus, model alveolus, and model of capillary. Capillary. Between them, barrier called membrane, lung membrane. It includes surfactant, surface, surfactant, alveolus wall, interstitial fluid, walls of capillary, plasma, and walls of erythrocytes. This barrier has 5 components. Surfactant, alveolus wall, interstitial fluid, capillary wall, plasma, and 6 components. The gas exchange includes absorption of oxygen and removal of carbon dioxide due to pressure gradient of partial pressure. Normal partial pressure of oxygen inside alveolus about 100 mmHg. It's less than atmospheric pressure because atmospheric air cannot fill all lungs during breathing. It's mixture between lungs, alveoli, alveolar gas, and atmospheric air. It's mixture. So partial pressure oxygen less than atmospheric. And opposite, partial pressure carbon dioxide more than atmospheric, about 40 mmHg. 140. Venous blood flowing into pulmonary capillaries has partial pressure oxygen about 40 and partial pressure carbon dioxide about 46. So we have pressure gradient between alveolar gas and capillary. What is the gradient? How many mmHg for oxygen? How many mmHg? Difference between this and this.
70.
60. 100 minus
60. 70 alveolar.
No.
70.
100.
100.
Alveolar. And 40 no? In venous
Equal
blood.
pressure in the
Pressure.
will be equal pressure in the alveolar and
Yeah, at first different. There's blood inflow to alveolus. Blood contains oxygen to provide partial pressure about 40. Difference 100 minus 40, 60.
60.
Great. What about carbon dioxide? How many mmHg?
6.
6. But it provides equal gas exchange because carbon dioxide is water-soluble molecules. Barrier membrane contains more water, so water-soluble substance goes across membrane easier. Oxygen is fat-soluble, it's difficult for it to go across barriers, so it needs more pressure. So, for example, in atmosphere, when atmospheric pressure decreases, for example, sometimes it happens here, 740, not 60, 40, 40. It decreases pressure oxygen, and some persons, especially age old person, has problem with condition due to problem with gas exchange and supplying blood with oxygen. And remember these numbers. It's necessary to memorize these numbers.
Condition.
After gas exchange, partial pressure in blood, oxygen becomes 100 equal alveolar pressure after gas exchange. It's arterial blood. Here venous blood, like venous from systemic circulation. Here arterial blood. Okay, 100. Yeah. Because the hemoglobin binds to oxygen. And what about transport cases? Oxygen is transported mostly 97-98% in binding to hemoglobin, oxyhemoglobin. Do you know this pulse oximeter? No?
Pulse oximeter.
Pulse
Yes.
oximeter. 96, 98, it measures this. And 2% soft. Because oxygen must travel across plasma, interstitial fluid. So a little oxygen is soft solution. But oxygen is fat soluble. It can go easily in free form. So it must have transport by hemoglobin. What about carbon dioxide? Carbon dioxide is transported again in combination with hemoglobin, aminohemoglobin,
20.
about 20%, no, 10-20%, depends on.
Each other.
About 7% free, soluble, and most bicarbonates.
Each other.
Bicarbonates. But bicarbonates are made, most of bicarbonates are made inside erythrocytes. Inside erythrocytes,
With H2O.
yes, inside erythrocytes, carbon
Cell.
dioxide plus water, carbonic acid, due to carboanhydrase. Carboanhydrase, very important, very important. Enzyme,
Enzyme.
it accelerates this reaction in 25 times. So inside blood, this reaction can be, but very, very slow. So erythrocyte very important. Well, transport gases, hemoglobin can release oxygen and remove oxygen, give oxygen into tissue, depending on some factors. These factors I can show oxyhemoglobin dissociation curve. Another curve, another graph. Oxyhemoglobin dissociation curve. What is it? What does it mean? Oxyhemoglobin dissociation curve. Partial pressure X. Partial pressure oxygen, millimeter Hg in the blood. Partial pressure oxygen. Axis Y. Oxyhemoglobin percent. The most highest point here 100%, but never 100%. Oxyhemoglobin is formed in the body. Never. Maybe about it, but never 100%. Just in a box, special box. So the highest point on my graph will be about 97%. This curve has S shape. form, S-shaped form, like a letter S, S-shaped curve. It's very important also, like this. Highest level of pressure oxygen in lungs, 100%. So here here blood has 97% oxygen hemoglobin. Here lung position. What happened in lungs? When blood travels across tissue, tissue cell take oxygen, and pressure becomes about 40 millimeter G, and it coincides with points given 75% oxyhemoglobin. Not all oxyhemoglobin releases oxygen into tissue. Just about 22%. So this release oxygen into tissue. Provide tissue, supply tissues. But this curve reflects affinity hemoglobin to oxygen. In some conditions, these curves may be shifted to the right, to the left, chakras, depends on some factors. For example, physical exercise, running, physical exercise, what happens? During physical exercise, blood contains more carbon dioxide,
More CO2.
Carbon dioxide, yes, decreases pH due to acidity, decreases pH, more temperature, not heating, body heating.
Hydrogen ion. Hydrogen, increase hydrogen.
Hydrogen increase, pH decrease. It shifts these curves to the right. Shifts curves to the right. And what can we see? In this case, higher point becomes decreased a little. Maybe not 97, 95, okay. But lower point becomes much lower. It provides a release of more oxygen release to maintain higher oxidation in the tissue. Metabolite needs to supply our tissues more. And opposites, decrease carbon dioxide, for example, at mountains, at high altitude, increase pH, alkalosis, or cold, can shift this curve to the opposite side. Breathing control, I don't have a lot of time, but it's necessary to explain. Breathing control, that I can't explain now. You will read in the textbook, listen to my lecture, video lecture. I try to explain the more complicated things, more important, more complicated things. Breathing control. Breathing control of lungs ventilation. I'm here, lungs ventilation. Control, regulation of lungs ventilation. Just regulation of lungs ventilation. Systemic regulation. At first, nerve center. Nerve center we can consider in local medium and in wider. Local medium is related to the one level of central nervous system provided control. Wider medium means all central nerve centers influencing this process. With brain, brainstem, pons, medulla, then hypothalamus, cortex, limbic system, cortex, limbic system, emotional, limbic brain, spinal cord, cervical segment, thoracic segment, lumbar not so good. Key muscles. To provide at least quiet breathing, a person uses inspiratory muscle, diaphragm, and intercostals, external intercostals. Diaphragm and external intercostals muscles. What part of spinal cord contains motor neurons innervating diaphragm, cervical or thoracic?
Что?
What part of spinal cord innervates diaphragm, cervical or thoracic?
No, cervical.
Cervical. This motor neuron located for innervating diaphragm is located in cervical. Motor neuron located intercostal muscle, located intercostal located in thoracic. Then, normal breathing. Experiment with transection of central nervous system. Normal breathing. For example, so an animal with narcosis, normal breathing. Then, if you transect here, nothing happened, normal breathing. Normal. If you transect here, what happens with breathing? Between cervical and thoracic, what happens with breathing? It becomes more or less? Less.
Yes.
Because intercostal muscle doesn't have time. Rate the same, but volume becomes less. Alright? If you transect brain here, what happens?
More. Volume more.
Between brain stem and spinal cord, what happens? Nothing breathing, no breathing. No. This conclusion, a main center providing pattern of breathing, cyclic breathing, is located in the brain. If you transect brain upper pons, again we have normal breathing. I mean here like animal without behavior, the whole direct behavior. Just background. Normal breathing again. Normal breathing. So main center is located in brain stem. If you transect brain stem between pons and medulla, you have slowing, decelerating of inspiration, expiration, both. Inspiration and long expiration. Then again, delay inspiration. Inspiration and great pause, and last transection at the middle of pons provide increase of time inspiration, then short exhalation and new cycle. So medulla contain minimally required nuclei. These nucleus are called DRG, dorsal respiratory group, and ventral respiratory group. Ventral respiratory group, DRG. It's a very complicated interaction between them. Dorsal respiratory group mostly is responsible to change breathing due to information receiving from receptors. And dorsal respiratory group influence on ventral and spinal cord. Ventral respiratory group influence on crane pattern, main pattern, background pattern, cyclic pattern. Okay, how does it work? Scientists in the previous century, 20th century, discovered a lot of types of respiratory neurons. Some neurons were active just during inspiration. Of course, scientists called them inspiratory neurons. Another type of neuron are fired during expiration, expiratory neurons. Some neurons were active between two phases, between expiration, inspiration, or between inspiration and expiration. There's different types, but we will consider it with simple scheme to understand the principle. Inspiration, expiration. We will draw another scheme to explain this process of pattern. Are you tired? Остальные ваши.
Professor, on Saturday we have class.
Yes.
We should memorize all this
No.
information.
Saturday blood.
Just class.
Blood.
So you sent us 54 page. 58, yes. You should.
It's life. But at first you know a lot about histology. Composition, blood composition, numbers, erythrocyte, thrombocyte, leukocyte. I wrote a question, more important question for our class. Leukocyte function, short, principal function, blood group types, and clotting. Because clotting was complicated. So, come back now. Scheme how this center works. There are a lot of types of neurons. They activated one time by the next one by one. New group inhibits previous group. It forms cycle. At first, start inspiration, then continue inspiration, then stop inspiration, and then start expiration. Just one by one. At first, one inspiratory neuron, they called inspiratory early neuron. Early means a first stage of inspiration. Start inspiration. Function start inspiration. They send signal to another inspiratory neuron. This neuron innervate directly motor neuron, diaphragm, motor neuron, and innervation of muscle, not muscle. Inspire diaphragm. Then inspiratory neuron or area stimulate another group. It's old scheme, but modern scheme very complicated. It's not important for us. Just understand principle. Another group inspiratory equal. Print. Inspiratory late neuron function is inhibition previous. Start this and together inhibition, recurrent inhibition. Because it happens and during this together increase of inhibition this time will stop inspiration. Then, during inspiration, inspiratory neuron inhibit expiratory neuron. I will not show here groups expiratory neuron, but because of expiratory neurons. Expiratory neuron has two functions. With slow firing, low firing, during low inhibition. Oh, sorry, minus, of course, minus. Minus. I will mark here. Here plus, here plus, here plus. Black minus. Expiratory neuron inhibits reciprocal inhibition, inhibits this and this. So during inspiration, expiratory neurons are inhibited. And this doesn't work. Yeah? We have inspiration, then we have inhibition. During inhibition, expiratory neuron becomes more and more active. They help to inhibit inspiration. When expiratory neuron has signal, additional signal from brain, higher stimulator influence, force, vital capacity, they innervate motor neurons of muscle responsible for expiration. Providing forced expiration. Passive expiration. Quiet breathing doesn't require expiration. Just force. But during quiet breathing, expiratory neuron helps to inhibit expiration. So this is a scheme of medulla. What does pons do? Pons has two sensors, acoustic center, here acoustic center, AC, and upper pneumotaxic center. Acoustic center increases inspiration, pneumotaxic center starts expiration, provides a faster expiration, and pneumotaxic center inhibits acoustic. So pons accelerates change of phases, accelerates start of inspiration and switch to expiration. So after transaction between pons and medulla, breathing becomes slower. Receptors. What receptors influence breathing? We can divide actually a lot of receptors more or less influence on breathing. We divide it to specific receptors of respiratory system and outside respiratory system. Specific respiratory system receptors, chemoreceptors and mechanoreceptors. Chemoreceptors are main receptors to control breathing. If you denervate chemoreceptors, this will work very, very slowly. It happens, for example, in newborn with problem of central nervous system. When newborn has problem during delivery, newborn child, his brain had hypoxia, and it becomes less sensitive to receptor signal. Receptors were located. The more important receptors are located in the medulla. Here are receptor zones, receptors, chemoreceptors, central chemoreceptors, central chemoreceptors are sensitive to hydrogen ion in cerebral spinal fluid, just here. It depends on carbon dioxide. As carbon dioxide goes across brain barrier, blood-brain barrier easily, hydrogen ion cannot go across blood-brain barrier. So just carbon dioxide. But carbon dioxide, due to carbon anhydrase, forms hydrogen ions inside cerebral spinal fluid. Well, carbon dioxide from blood goes inside brain and provide activation of central chemoreceptors. They accelerate inspiration. Peripheral chemoreceptor, less sensitive. Peripheral chemoreceptor located in the same zones like baroreceptors. Where baroreceptors? Where baroreceptors? Second colloquial, where baroreceptors? What blood vessels?
Aorta and
Aortic
carotid
arch
sinus.
and carotid sinus. And near them chemoreceptor located, secondary receptors. Peripheral chemoreceptors are sensitive. Peripheral chemoreceptor, it's very important last fact, if I will explain. Peripheral chemoreceptors, peripheral chemoreceptors, aortic arch and carotid sinus. Peripheral are sensitive, again, increase carbon dioxide in blood, acidosis, and decrease partial pressure oxygen, but high decrease where partial pressure becomes less than 60 millimeter Hg. Normal 100, decrease less than 60 millimeter Hg. For example, at high altitude in mountains, 2,500 meters, it becomes like this. So, what factor more important to control breathing, carbon dioxide or oxygen?
Carbon dioxide.
Carbon dioxide is very important fact. You must memorize it. Why? Because in accordance with chemistry, oxidation of oxygen provides carbon dioxide. If carbon dioxide becomes high, it blocks this response, independently, regardless of oxygen. So your presence, and then you can be free.